नमस्ते बच्चों, myself Om Prakash Kesari, faculty of Department of Mathematics under Faculty of Education and Methodology. Today I'm going to deal with conformal mapping, which is which are a very important chapter of complex analysis, which are taught in BSc, B.Ed, PCM, 8th semester student. These are the lesson plan, which are already discussed in your previous class. These are the steps for planning a lesson. These are the components of lesson planning. Today I'm going to deal with the complex analysis under which we have taught you today a new chapter named conformal mapping and binary transformation, which are the subject of BSc, B.Ed, PCM, 8th semester student. Today I'm going to introduce some basic concept related to conformal mapping, that is introductory part of the conformal mapping. In this chapter, we deals with the closed loop at mapping properties of an analytic function in a complex value function. Throughout this chapter, all the curves z of t are assumed to be such that dz by dt is not equals to 0 for all t. dz by dt is not equal to 0 for all. Now, before starting the chapter, we are going to define some basic terminology. One of them are conformal equivalence. Before defining the conformal equivalence, we define some angles and between two curves. Suppose two smooth curves C1 and C2 intersect at Z0. Then the angle formed C1 to C2 at Z0 is angle C1 or angle C2 and is defined as the angle measured in counterclockwise from the tangent line of C1 at Z0 to the tangent line of C2 at Z0. That means in this curve is C1 and that one is the C2 curve. When we want to find the angle between these two curves, we first at a point Z0, we first draw two tangent line at C1 and C2 respectively and measure the angle between these two tangent line in counterclockwise direction. This angle is called the angle between the two curves at the point Z0. Now we are going to define that the function, when a function is said to be conformal at a point. Suppose f is defined in the neighborhood of Z0. If f is said to be conformal at Z0, f is said to be conformal at Z0 if the function f preserves angle there. That is, for each pair of smooth curves C1 and C2 intersect at Z0, then angle C1 or angle C2 is equals to angle gamma 1 or angle gamma 2, where gamma 1 is equal to f of C1 and gamma 2 equals to f of C2, where gamma 1 and gamma 2 are to any curves. Similarly, we can say f is conformal in region D if f is conformal at all point. F is conformal at all point Z belongs to the domain D. Now we are taking an example. Let us consider a function f of z equals to z square, which is not conformal at z equal to 0. For example, the positive real line axis and the positive imaginary line axis are mapped onto the positive real axis and the negative real axis respectively. However, as we see Below that, it is conformal at all other point of the complex plane. Now we are going to define some more basic terms which are locally one function, which are locally one function in a domain D in at a point and in a region D. Before going to define these terms, we first define one function. When a function is mapped from both sides, from domain to codomain and codomain to domain, and each element of a domain has one and only one image in codomain, and each element in codomain has one and only one image in domain, then the function is said to be one function. And here, for the complex valued function, if f is locally 1 at z0, if for some delta greater than 0 and any distinct z1 and z2 belongs to d of z0 delta, d of z0 delta, that means delta neighborhood of z0. And then we can say that f of z1 is not equal to f of z2 at that point. F of z1 is not equal to f of z2. That means for some delta greater than 0 and any two distinct points z1 and z2 which are belongs to the delta neighborhood of z0, then f of z1 is not equal to f of z2. Then we can say that f is locally one function at z0. That means f is locally 1 at the point z0. Now we are extend this definition to a region. F is said to be locally a 1 throughout a region f if f is locally 1 at every z belongs to D. That means no any f of z is equal to another f of z. That means f of zi is not equal to f of zj, where I is not equal to j, and zi belongs to D. Similarly, we can define this in a region. If f is 1 function in a region D, f is a 1 function in a region D if for every distinct z1 and z2 belongs to D, f of z1 is not equal to f of z2. F of z1 is not equal to f of z2. Then we can say that f is a 1 function in a region D, not locally 1. Now, these can be shown with the help of an example, which are already seen in the web example. F of z equals to z square and is not locally 1 at z0, since f of z equals to f of minus z. That means f of z1 is not is equal to f of z2, which contradict the definitions of the locally 1 function. And however, f is locally 1 at all points except the point z equals to 0, which are already seen in the previous example. Now we are going to study one more important theorem on locally 1 function. Suppose f is analytic at z0 and f prime z0 is not equal to 0, then f is conformal and locally 1 at z0. That means we can say that if f is analytic at z0 and f prime z0 is not equal to 0, then the function is conformal and locally 1 function at z0. The proof of this theorem is leave for you for an exercise. This session powered by the digital version 2.0 Jyoti Vidyapeeth Women's University, and I hope you are satisfied with my digital session. If you have any queries, please mention in comment box. I will try to solve it. Thank you.